Hi, everyone. All right. Before we get going on actually doing thermodynamic variable manipulations, I just wanted to finish off one last topic connected with what we were doing last time, which is, if you recall, we had looked at the heat capacities, the heat capacity at constant pressure, the heat capacity at constant volume, and we showed that their difference was N.K. Boltzmann. And I wanted to pick up from there very briefly and just say something about adiabatic processes, because we got to that point by talking a little bit about constant volume processes. So this time I want to talk about an adiabatic process. And this is adiabatic in the thermodynamic sense, not in the quantum mechanical sense. So for an adiabatic process, just to refresh your memory, that means there is no heat transfer. And again, we're going to assume that we have constant particle numbers, so I'm just going to set that to be 0. dn is going to be 0. If there's no heat transfer, this first term is also 0, so we just have that dE is minus p dV for an adiabatic process. The only way the energy of the system can change is through work. Now, we've already shown we're going to worry about an ideal gas for the moment. So for an ideal gas, we already showed that the energy is really just dependent on the temperature. We showed that last time. And that means that dE would have to be CV dt for the case of the ideal gas, right? I don't want to overly generalize. So if that's true, we have that situation. Now, what else do we know? What we want to do here is figure out what happens during adiabatic processes. I kind of dropped the answer on you in a previous lecture. I told you, I asserted a certain fact, and I'm going to now derive it, right? So this is our change in energy. Now, what else do we know? Well, if we have an ideal gas, we also have that PV equals N.K. Boltzmann T, and we can consider variations of our variables, right? We're still going to keep n fixed. But if we consider variations, then what do we have? We're going to play games with differentials here. So we're basically going to have dP times V plus P times dV. So that's the variations that can happen on the left-hand side if we consider small independent variations of these things. And that has to equal N.K. Boltzmann dt, right? So if I substitute this into up in here and we rearrange terms, what are we going to find? When we do a little bit of algebra, we are going to find dV over V times CV plus N.K. Boltzmann. So all we've done is group the dt terms, this one and that one. And we're going to say, if we just rearrange things a little bit, we're going to get minus CV dP over P, right? So this is an interesting differential equation here. So all I've done is rewrite that on the top of a new slide, and what we can do is we can do again a tiny bit of calculus. We can define gamma as Cp over Cv. We know that this collection of things is Cp. We learned that last time. And so gamma here is the ratio of heat capacities, or the ratio of specific heats. And if we look at this equation, what we find is that this equation implies the following thing. It implies, we can integrate both sides basically. It implies that PV to the gamma equals a constant. And again, just to remind you, this is for an ideal gas, adiabatic process, no heat transfer. So this is the thing that I told you a couple of lectures ago, that it was true, and I didn't justify it at all. Well, now we've seen how you can justify it. You're assuming the first law, you're assuming things are adiabatic, you're assuming constant particle number, and you're plugging in the ideal gas law, an equation of state. in sort of our informal definition of equation of state. I'm doing a little bit of math. Now, the other thing I should point out, it's trivial to, you can use the ideal gas law again, and you can get other forms of this expression that are equally true. You can have, for example, TV to the gamma minus 1 equals a different constant during an adiabatic process, just by using PV equals NKT. Or if you really want, you can use TP to the 1 minus gamma over gamma is a constant. These are all just playing games with the ideal gas law and shuffling around which variables you have. But it's just interesting to note you get these power law variations when you're dealing with a system that is an ideal gas and there's an adiabatic process, an adiabatic change in volume going on. Now, something to know, gamma for a monatomic gas ends up equaling 5/3, right? That's because the heat capacity at constant volume for the monatomic ideal gas, I told you this last time, is 3/2 NK Boltzmann. And that means, because Cp is Cv plus NKB, that means that the heat capacity at constant pressure is 5/2 NK Boltzmann. And so the ratio of 5/2 to 3/2 is 5/3. For diatomic gases, which is really directly relevant for things like air, what you find is that gamma is 7/5. So why is the heat capacity at constant volume for a diatomic gas bigger than for a monatomic gas? The answer is, if I have a diatomic gas, here's my little ball and spring picture of a diatomic gas molecule, I have additional degrees of freedom. I've got the vibrational degree of freedom that way, and in principle I also have the rotational kinetic energy where the molecule can be spinning in space. So that's why for a diatomic gas you get 7/5, and for polyatomic gases you get even higher, ratios of larger numbers. But if you have all sorts of internal degrees of freedom for your gas molecules. Just to give you a sense of scale, by the way, if you use the diatomic gas case for air, you can actually think about the way your car works. I mentioned this a while ago. If you want to worry about a diesel car, so in the cylinders of your car, what you find is that V initial over V final, so this is basically what's called the compression ratio for a typical diesel car, is something like 8. So the final volume of the gas in the cylinder is an eighth of the initial volume. And what happens is that the cylinder, the piston compresses the gas quickly enough that the gas does not have time to conduct a lot of heat away through the walls of the cylinder. And so it turns out that if you start with the air fuel mixture in the cylinder at around 25 Celsius or room temperature, when you compress things this much, you can end up getting up to about 500 C, right? So that's why in a diesel car you don't even need any spark plugs. You just compress the gas quickly enough that just the adiabatic compression is enough to get the mixture hot enough to ignite. By the way, if you've ever had a car that knocks or does what's called dieseling, which is when your car keeps running even though you've turned off the ignition, that is this sort of very large temperature increase that happens because you're compressing gases adiabatically. All right, I'm going to stop there for a second, and I'm actually going to switch to a separate YouTube video to talk about the thermodynamic variable manipulation, just because it's kind of nice to have things broken up by topic.